A-level statistics, permutations and probability. We can use the work we've been doing on permutations and combinations to solve probability problems. Now we have that if all outcomes are equally likely, then the probability of an event happening is equal to the number of favourable outcomes over the total number of outcomes. Now this leads to problems involving selections. Let's look at an example. Example 1. The letters of the name Hannah are arranged in a line. In part A, we're asked how many different arrangements can there be? Well, to solve this, there are 6 letters, and there are 3 pairs of letters that are equal. So the number of arrangements are 6 factorial over 2 factorial times 2 factorial times 2 factorial. Now this is 6 times 5 times 4 times 3 times 2 times 1 over 2 times 2 times 2, which cancels to leave 90. So the number of arrangements is 90. In part B, we're asked, what is the probability the middle 2 letters are the same? Now, for the middle 2 letters, there's 3 possibilities. They could be NN. Now that means the other 4 letters can be rearranged in any way, but there are 2 pairs of letters the same. So it's 4 factorial over 2 factorial times 2 factorial, which is equal to 4 times 3 times 2 over 2 times 2, which is equal to 6. If the 2 middle letters are A and A, we have the same situation. There are 4 letters left behind, and there are 2 pairs of letters that are equal. So again we get 4 factorial over 2 factorial times 2 factorial, which works out to be 6. And then we have the 2 middle letters could be H and H. And this is identical. There are 4 letters left over, again with 2 pairs of equal letters. And so we get 4 factorial over 2 factorial times 2 factorial, which again works out to be 6. So the total number of arrangements is 6 plus 6 plus 6, which is 18. So the probability the middle letters are the same is 18 over 90, which cancels down to give 1/5. Now in part C, we're asked what is the probability the letters are the same if we go left to right or go right to left. Now to solve this, the number of ways the letters are the same left to right as right to left is equal to the number of ways the 3 letters H, A and N can be rearranged. The remaining 3 letters have the same order, but in reverse. Now that's 3 factorial, which is 3 times 2 times 1, or 6. So the probability is 6 over 90, or 1/15. So the probability left to right is equal to right to left is 1 over 15. Let's have a look at a second example. A boy has 8 pop music CDs, 5 jazz music CDs, and 6 classical music CDs. Going on holiday, he wants to take 3 of each type of CD with him. In part 1, how many ways can he take 3 pop music CDs? Well, to solve this, the number of ways of selecting 3 out of 8 pop CDs is 8C3, which is equal to 8 factorial over 3 factorial times 8 minus 3 factorial, or 8 factorial over 3 factorial times 5 factorial, which cancels down to 56. Now we could have got that by typing in 8C3 onto the calculator. So there are 56 ways of selecting 3 pop CDs. Now in part 2, how many ways can he select 3 pop, 3 jazz and 3 classical music CDs? Well, to select them, it's going to be 8C3 pop CDs times 5C3 jazz CDs times 6C3 classical music CDs. Now that's 8 factorial over 3 factorial times 5 factorial times 5 factorial over 3 factorial times 2 factorial times 6 factorial over 3 factorial times 3 factorial. And that works out to be 56 times 10 times 20, or 11,200. Again, we could work that out on a calculator by typing in 8C3 times 5c3 times 6c3. So there are 11,200 ways of selecting 3 of each. In the end, he packs in a hurry and just takes a random selection of 9 CDs. What is the probability that he does take 3 of each type? Well, the total number of ways of selecting 9 CDs is 19C9. There are 19 CDs altogether, and he's taking 9. So that's 19 factorial over 9 factorial times 10 factorial, which works out to be 92,378. So the probability of selecting 3 of each is the answer from the last question, 11,200 over 92,378, which does cancel down to 5,600 over 46,189, or as a decimal, that's 0.12140988. So our answer, rounded off to 4 decimal places, is the probability that he packs 3 of each is 0.1214. In example 3, we're told 4 boys and 3 girls sit randomly in a row of 7 chairs. In part A, we're asked, what is the probability that there are no 2 boys sitting next to each other? Well, to solve this, the total number of permutations of 7 children in 7 chairs is 7 factorial, which works out to be 5,040. Now, if there are no 2 boys together, they must be arranged boy, girl, boy, girl, boy, girl, boy. So there are 4 boys arranged in 4 seats and 3 girls arranged in 3 seats. So the number of permutations is 4 factorial times 3 factorial, which is 24 times 6, which is 144. So the probability there are no boys sitting together is 144 over 5,040, which is 1 over 35. And that's our answer. The probability is 1 over 35. Now in part B, we're asked, what's the probability that all 3 girls are sitting together? Well, if the 4 boys sit down, they can be arranged in 4 factorial ways. Now we've got a diagram of the boys with underlined spaces between them. If all the girls sit together, there are 3 factorial ways they can be arranged. Now the group of 3 girls can be put in any one of the underlined spaces. That is, in one of 5 positions. The girls can be arranged in 3 factorial ways, because there are 3 girls. The boys can be rearranged in 4 factorial ways, and the girls can be placed in one of the 5 spaces. So the number of arrangements is 3 factorial times 4 factorial times 5, which is 6 times 24 times 5, or 720. And so the probability that all the girls will sit together is 720 over 5,040, which cancels to 1/7. So our answer is 1/7. In example 4, we're told a box contains 10 sweets. They're covered in chocolate and look the same. 3 are mint and 7 are toffee. A boy chooses 4 sweets. What's the probability that he gets 3 mints? So to solve this, if we consider all the ways the sweets can be arranged, there are 10 sweets of which 7 are the same and 3 are the same. So the number of ways they can be arranged is 10 factorial over 7 factorial times 3 factorial, which is 10 times 9 times 8 times 7 factorial over 7 factorial times 3 times 2 times 1, which cancels down and leaves 120. Now, let's lay out the sweets in a row with the 4 he's chosen coming first. So for example, it might be mint, toffee, mint, mint, and then toffee, 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 toffee. Now the number of ways the 3 mints can be arranged in the first 4 places and the 6 toffees in the last 6 places is 4 factorial over 3 factorial times 1, which is 4. So the probability that he chooses 3 is 4 out of 120, or 1 out of 30. Now we're asked in part B, what's the probability that he chooses 2 mints? Now the number of ways 2 mints can be arranged in the first 4 places is all the rearrangements of MMTT times all the rearrangements of MTT-TTT, which is 4 factorial over 2 factorial times 2 factorial times 6 factorial over 5 factorial, which is 4 times 3 times 2 over 2 times 2 times 6 times 5 factorial over 5 factorial. Well, that cancels down a lot and leaves an answer of 36. So the probability that he chooses 2 is 36 out of 120, or that cancels down to 3 over 10. Now in part C we're asked what's the probability that he gets 1 mint. Well, the number of ways 1 mint can be arranged in the first 4 places is the total number of ways that MTTT can be rearranged times the number of ways that MMTTT can be rearranged. Now there are 4 numbers in the first part, of which 3 are the same, so that's 4 factorial over 3 factorial, and in the second part we've got 6 numbers with 4 the same and 2 the same. So that's 6 factorial over 4 factorial times 2 factorial. And if we write that out, it does cancel down a lot and leaves 60. So the probability he chooses 1 is 60 over 120, or a half. And in part D we're asked what's the probability that he gets no mints. Well, the number of ways no mints can be arranged in the first 4 places is the rearrangements of 4 t's, which is just 1, times the rearrangement of 3 m's and 3 t's. So that's 1 times 6 factorial over 3 factorial times 3 factorial, which is 6 times 5 times 4 times 3 factorial over 3 times 2 times 1 times 3 factorial, which cancels down and leaves 20. So the probability he chooses none is 20 over 120, or 1 over 6. In example 5 we're asked, if the letters in the word total are arranged randomly, what's the probability the letter A is in the middle? Well, to solve this, consider the 2 t's as different letters, t and t dash. The total number of arrangements is 5 factorial. If A is in the middle, there are 4 letters and 4 spaces. So the other letters can be arranged in 4 factorial ways. So the probability that A is in the centre is 4 factorial over 5 factorial, which is 4 factorial over 5 times 4 factorial, which is 1/5. So the probability A is in the middle is 1/5. In part B we're asked what's the probability that the letter T is in the middle. Well, if T is in the middle, there are 2 choices for the middle, because we've got 2 T's. And then we have 4 different letters, so we have 4 factorial choices for the remaining positions. So the number of arrangements is 2 times 4 factorial. So the probability that T is in the middle is 2 times 4 factorial over 5 factorial, which is 2 times 4 factorial over 5 times 4 factorial, or 2/5. So the probability that T is in the middle is 2/5. In part C we're asked to find the probability that the 2 letter T's are not next to each other. Now we can lay out the letters O, A, L with spaces between them. Now the letters O, A and L can be rearranged in 3 factorial ways. The T's can then be put into 2 of the spaces. We are selecting 2 out of 4 spaces for the letter T. So the number of ways is 4p2, which is 4 factorial over 2 factorial, or 12. So the total number of arrangements is 3 factorial times 12. So the probability that there are no T's together is 3 factorial times 12 over 5 factorial, which is 12 over 5 times 4, which is 3/5. So the probability that there are no t's together is 3/5.